SwayamPrabha. Digital India. Educated India.
So good morning. Good morning. So there's a beautiful lecture before mine on quantum probability. I would say quantum mechanics or quantum computing, quantum probability, whatever. And today I have two lectures, and you people are students, so you put every subject in a cabin. So there's one thing called maths, one thing called physics, one thing called chemistry, and thou shall not mix. Okay? And reality is completely different. They all mix with each other. So my first lecture can be thought of as a lecture in mathematics, and the second lecture can be thought of as a lecture in physics. But personally, I don't see any distinction. It's just one lecture, one sort of. I'm giving two lectures, but okay. So we will start with the basic idea of probability. Since you had a lecture on quantum mechanics, this is what is called as classical standard probability, which you probably have in school. Right? Have you people done, or it's in 12th standard? You're done probability. Okay. I don't need some fancy. And if you don't know any probability also, we can, you will learn. So again, I should explain to you what classical means. Classical doesn't mean like in literature. Classical literature is like Shakespeare or some, in classical Tamil literature, some old stuff. It's not that. In physics, it means not quantum. Okay, classical means not quantum. Okay, so of course we will begin with the classic example. So the first example is a very simple one. You toss a coin. And it has how many outcomes? Two outcomes. And we call them heads or tails, right? So two outcomes. So S stands for sample space, which is just the set of outcomes, nothing. Okay. So the second example is you toss a die. Okay. So English is a funny language. This means two different things. But most of you probably know the plural of this word. What is the plural? Dice. Okay. A die or a dice. Okay. So what is the sample space here? 1, 2, 6. Okay, so these are the kind of things. So you're doing some kind of experiment, and these are the possible outcomes. But we can do more things. We can toss n coins. N is too big, so I will just write, okay, let's do it. Toss n coins. Okay. So now the sample space is quite big, right? It is 2 power n. Okay, so S be all heads, and there are a whole bunch of choices to all tails. And the size of S is 2 power. Okay? We could do a different experiment, which is toss one coin n times. Okay? What is the sample space here? Same as above. Okay? So there are a few characteristics which you would expect when we are doing this kind of experiment or this kind of experiment, is that we would suppose, I mean, we don't know if the coin is fair or not, etc. So, but the way, how would we determine if the coin is fair? Equal probability, okay. So the idea is that what do we expect in these things? We expect that half of them will be heads. Okay, so the expectation okay. Now comes so this, we can go ahead and I have a coin. I want to do experiment number 4. I'm tossing it 5 times. Okay. So now what would you expect? I mean, if you do the experiment, you can get anything. Yeah, you could get a fair coin, and 5 tosses can lead to 5 tails. You're not guaranteed that the coin is not fair. Okay. So I mean, at least, so we should make this more precise, is when as n becomes suitably large. Okay. Or we would like to say that there's a window. So let's just focus on the number of heads. And we know that, sorry, I'm running out of space, so I'll use this bottom part. And I love interruptions. Okay, so let's just draw some sort of a number line 0 to n. And we have n by 2 here. And we would like to think that there is some space, call this delta and delta. So we will let things be in a window which is not just, which goes something like this: n by 2 minus delta, n by 2 plus delta. This is sort of a much more realistic explanation of what we should expect. And the question would be, how do we estimate what delta should be for 5? Okay, some estimate will tell you that delta can be, so we will see that the estimate is going to be something like root n. Okay, we'll figure it out. Even if we don't, it's okay. So this is the kind of things you want to do, but there's no notion of probability yet. It's just asking what are the bunch of outcomes, and we want to map things to probability. Okay. So are there any questions or even comments at this point? Yeah.
Actually, in the previous debate, they were asking how you can for sure measure a coin, whether it will land on the head or whether it will land on the tail.
Yeah, the thing is, it's landing this way is very rare, so I'll forget it. Oh, no, this is all classical. There's no, my coin is not a quantum coin yet. Yeah, but I will tell you what it means to make it a quantum coin in just probably 2 minutes. But I will not answer questions on quantum probability because that's not my goal today. Okay. So, man, why is this so hard? Okay. So the first step in all these things is this sample space can be random things. And we could have a sample space also as, the cat is alive, cat is dead. Right? I can have a sample space like that. But if you think about it, I mean, it's not too different from the first one where you toss a coin, head and tail. I could say head is cat is alive, tail is. So it shouldn't matter. So what one does is to map So one has the idea of a random variable. So what you do is you take a map from, this is some map, to some set, which will be the real line or some subset of it. Say R. Okay, R is the symbol for real line. Okay, you all know this, right? Yes. Okay, so this is just nothing but. Okay, but there can be more cases where instead of just putting it on a line, you can put it on a plane, you can put it in 3 dimensions, so R power n, all those things. But for today's lecture, we will only have R or some subset of R. Okay, so so let's just take our first example. And so what I can do is that H is mapped to 0 and tails is mapped to 1. Okay, but really I don't have, I mean it doesn't, I mean I could have mapped it to, as long as I don't map it to the same value, I'm okay. Okay, so but this is a choice of this map. Okay, and then so now what is happening is that the space set of outcomes is now mapped to points on the real line or points in the set. Okay, then you can do for instance answering like how many tails did we get. Okay, it's a very simple thing. You just if you toss it each time, you keep adding the numbers. So what's happening is that this kind of question is reduced to just mathematical addition of numbers. You couldn't, I mean you're not adding anything here, the 0 and 1, but if I wanted to count heads, I could have done 1 and 0. But okay, I chose it to be 0 here, so that's why I shifted suddenly to tails. But even then, if I know, so you can, so this is the kind of things. So this is the first idea, okay? And what is a random variable? So we'll use a symbol X, this is capital letter, okay? X is, in this case, so it is just the values, so X would be, if you wish, the image under map, the set goes to something, okay? And X, so this is the set of values it can take, and we will use X belongs to capital X. Little x is the values it can take. Okay, so in this case, what can little x take values? 0 and 1. Okay, so in our example here, okay, so this is the first idea of creating a random variable, because this space is measurable. We can add, we can multiply, we can do lots of things. Okay, one more thing to realize: if someone else shows 2 other numbers, I can always take linear combination. So I can do a second map. So somebody did this, I can go take a second map prime from R to R prime, and you can see that I can always make them map to each other. Change of variable would be some AX plus B. For some A and B, I can map 0 to -1 and 1 to 1, for instance. So they're all equivalent, so I can make some changes. So it's so in that sense, but X as we define will be given. I have to fix the map, and then I will get the answer. Okay, is this clear? Caps for the random variables. Okay, so the next step is to assign a probability to every x. Okay, and call this P of x. Okay. Is this picture clear? So this is the setup of probability. And what are the properties that we will expect from a probability? Now this is something you know. What are the properties of P? Huh? They add up to 1, okay. Is that all? Any other property? It can't be negative. It can also be equal to 0. Let's let that. So these are the only two conditions. So call this 1 and this is 2. This is saying that the total probability is equal to 1. Okay? So in this corner, I'm going to tell you what quantum probability is. And it's going to be a corner because I will not discuss a lot about it. Okay? So it's just, and I won't talk about probability, how a probability is assigned, but I will just tell you the first step. Here, for when we went to a random variable, we map the sample space to, say, the real line. Okay? So what you do is, in quantum probability, quantum mechanics or quantum probability, you take the sample space, okay, and you map it to a bunch of vectors. Some vectors. And you all know that we know how to add vectors. I don't know how to, so let's just take the case of heads and tails. So what I do in this, I'll map head to some unit vector. You know what a unit vector is, right? A unit vector EH. And I will map this to a unit vector T. An arbitrary vector in there. So now what's happening is that if you get in the sample space, I'm getting vectors. So here I don't know how to add vectors, but here I do. Because it's this. Most general vector will be some BH okay. So instead of heads or tails, now you go back to what I think Siddharth discussed. We take cat is alive, cat is dead. Now you get two states. So this is the state. He would have called this the state where the cat is alive, and this is the cat which is dead. And he would have written some 1 by root 2, etc. I have to explain the probability, I won't. Okay, but I just want to tell you is that you start from the same sample space, but what space you map into is where, yeah, it's into some space. It's called a vector space. Okay, so, but it's just this idea. Okay. How probability is assigned, what are the rules of probability are completely different. Yes. Very weirdly, this is a very, you want to, so mathematicians use this. You have a group, if you have a set with some properties are provable where you do this map, you prove it here. You want to find properties of this map, of this set, they figure out, they reduce it to a problem in this space. Sometimes this works better than actually doing the proof in S. So that's a very common trick, by mathematicians. They don't call it quantum mechanics, of course. Okay. No, yeah, all those things I said, I didn't discuss the second part, right? Assignment of probability, etc. So that will take me way off course, so I won't. Maybe someday I'll do that. Okay, good. Okay, very nice. Okay, so we'll come back to this. So there are only two parts to this whole story. Okay. Last idea which I need is that suppose I have two coins, I toss, and let's say they are identical. The point is that if I toss coin 1 or coin 2, the outcome of coin 1 will not influence the outcome of coin 2. Okay, this is the idea of independence. But there can be events where if something happens, so for instance, suppose I toss, a pair of dice. Okay, and then we ask the question, what is the probability of getting an odd number? You'll get something, or probability of getting 3 as the sum. Okay, but then we can, if you're given additional information that one of the die gave an even number, that these two events are correlated, because we know that if you got a sum as an odd number, if one of the die is even, you're guaranteed that the other one will be odd. So these are events which are not independent of each other. But the idea of independence is something which I will use. Okay, so we expect in examples 3 and 4 that the outcomes are independent. Okay. So more generally, you would say that, if you give me two random variables x and y, I'm generalizing it. We know how to go from that sample space to some variables. Okay. We say that, so more generally we say random variables x and y are independent when we mean exactly this. Okay, if you know a little bit of joint probability, it says that suppose, let's say that then little x belongs to this. Okay. We will have p of xy, which will say that capital X takes value little x, this will take value little y. And the idea of independence, so let's also keep track, okay, or we'll put subscript here now to indicate that there are two variables, and this, if we put in independence, what it says is that if I know the value of y, it doesn't change the story of x. If I know the value of x, that's the key, right? So this will just tell you that it's a product. Independence is required. Okay? If it is not independent, okay? So this is not true. Left to right reads only true when they are independent of each other. That is nice factorization happens. Not true in general. Okay. Are there any questions out here? A very, very simple idea, not fancy. So now let's revisit one more idea, which is from physics, not from mathematics. Like I said, there's no cabins. We would like to say that 3 and 4 are the same, right? 3 was tossing n things, n independent coins, identical coins separately, while the other one was tossing one coin. Okay, so we expect examples 3 and 4 to be the same. Of course, sample spaces are the same. That's a necessary condition. But what I'm saying is much more. Okay, and so example 3, we will call it ensemble. And if you're finding average values like how many heads, etc., so we'll use ensemble average. I will define this also. But ensemble in French means collection of things. So here it's a collection of 50 coins if n is 50. Okay. The 4 is called the time because it turns sequentially. So there's a time. Okay. So the statement is, we will define these things in a moment. What it says is that you expect ensemble average to be equal to time average. Okay. And this expectation need not be true. Okay. But in this example, yeah, our intuitive explanation is correct. And the equality requires, in more complicated settings, it assumes something called ergodicity. In lecture 2, we will see what that means. Okay. It requires something like that to be true, but it requires something even weaker than that, but let's put this and leave it out. Okay. So this is the kind of things that we have. Okay. So, sorry, I'm giving you a whole bunch of ideas, but each of them are not very complicated. But if you want to go deeper in all these things, you need to put in effort. But at this point, we don't want to go deep. Okay. So let us now go through our examples and do the assignments of probabilities, etc., and see what we get. Okay. So let's do that. Go back to visiting our examples because I didn't do the assignment of probability yet, except for nothing I have done. Okay. So let's revisit. So now, we'll go through our examples, and if I mix up 1, 2, 3, 4, please correct it. Okay. So 1 was just a coin toss, right? Okay. So now I'll just use the symbol P for P of H, and but P of T, 1 minus P. I don't need to introduce something else because total probability has to. Okay. And we also know P equal to half for a fair coin. Okay. Okay, now the sample space is 1, 2, 3, 4, 5, 6. Okay, and if it's a fair die, let's make it a fair die. It says that P1 equal to what? 1 by 6. Okay, good. Now let's get to 3 and 4. I'll do it in one go. We have tossed n coins. Okay, so what is the assignment? So let's okay. So now let's do a little bit of work. Let's take n to be 2. Okay, so let's do special case, n equal to 2, and ask what PHH should be. And it's this coin. What should PHH be? Huh? No, let's not assume P equal to half for a fair coin. I want arbitrary P. We'll see an example where P is very small. Okay, later. What should it PHH be? First thing is these are independent of each other. Okay, and this is little p. Which somewhere, I mean, if you put this equal, p equal to half, you will get 1 by 2 square as somebody just said. Okay, but we can write a few more things. What is this equal to? No, I don't want for 1 by 2, I want for arbitrary p. P into 1 minus p. P of t will be the same. No, that's not equal to this, sorry. Even I made the mistake, p equal to half. They are not the same. Okay, so but this is a little messy. Quite often we are not particularly interested in getting, asking, we are only interested in number of heads. Okay, so let's do this. So to differentiate between little p, I'll define, let capital P, little n be equal to the probability getting from n tosses. Okay. So let's look at this. In this example, maybe we can even keep the subscript to remind ourselves how many tosses we did. So we can see from here that P2 of 2 is P square from that, right? But what is P2 of 1? Huh? So there are two ways of getting it, HT, PH. Of 0 heads. Okay. So a little bit of combinatorics or binomial coefficients, binomial coefficients is useful in this context, and I'll write it in a suggestive fashion. I know you people write 2C1, but in modern, for at least 50 years, this is what is being used. Okay. So please learn to use modern notation, even though our textbooks don't, because I think you still use books from the early 20th century when factorial is written this way. No, you people have given up that. Oh, thank God. Exclamation, yes, okay, good. Okay. So now comes there will be some numerical factor, but one thing we know is that if I want little n number of heads, if I choose a particular sequence, I know it will come with p power n. But now it's not enough to do this, the rest of it better be tails. So it has to be 1 minus p power okay. What is the prefactor? So you think of, this is the following picture to have in mind. I have some n boxes and I have to put little n heads into this, and the rest will be. That is n choose little n. Sorry, I should have chosen R or something like that, you know. Okay. Fun exercise. Starting from this, show that total probability will add to 1, of course. What I am saying here is that, okay, so it comes from some simple, so this has a name, this particular, there's a particular distribution, it's called the binomial distribution for obvious reasons. Okay. Are there any questions? Anybody doesn't understand why I put this number out here? Okay, the pigeonhole idea will tell you this. You just have to, from capital N boxes, you pick little n. How many ways you can do that? Each one will be distinct. And they're all equally probable, that we know. Okay. So, one thing you can see here is that I have kind of forgotten about tosses out here. I don't need to really say, it's just some distribution where the sample space, now I can just think of it as x itself, capital X, which takes values from 0 to n. 0, it is just a set X. Okay, so now I can give you other examples. Another example which I'll give you in a moment. Okay, so this is called a this is an example of a what's called a probability even though I started tossing coins, I did some generalizations out there. I said I will not assume that my coin is fair. It can be anything, and I put a parameter and I got something. Okay, so I'll give you another example called the Poisson. One more thing is, if you are going to be in science, maybe one infinitesimal fraction of these you people will do science, because everybody does engineering or medicine, right? Nothing else. Everything else is stamp collection or something like that. Though I must tell you, I mean, I enjoy doing physics as much as I did when I was your age. It's still fun, maybe more fun, I don't know, but I still have fun. Okay, and they pay me for it. That's the best part. The reason is that all these, you'll find a lot of French names coming in maths and physics, because they made lots of contributions. So Poisson is the name of a person, but Poisson also means fish in French. So he is fish. His last name is Fish. Okay, so you should learn how to pronounce their names. Nowadays there's YouTube, etc. to tell you how to pronounce names. Okay, so the Poisson distribution, I'll tell you, I won't worry about sample space, etc. I'll start with capital X. So X can take values from 0 to infinity. All positive natural numbers, including 0. Okay, and now I just have to give you what this probability is. It has one free parameter, lambda, which is like p. Okay, it has lambda is a free parameter. Okay, and we can check now that this is properly normalized. What is this summation equal to? People know what this is? E power. How many of you have seen this? Okay. How many of you know about the exponential function? Hopefully that set is larger. Very nice, very nice. Okay. So the exponential function is the following function which satisfies the following differential equation. Take a function, take its derivative, it's equal to itself. Okay, and there is one condition, f of 0 equal to 1. Okay, so mathematics is wonderful because it tells you that if you solve this differential equation subject to this thing, the answer is unique. So it defines that function. Okay, and this function then f of x is written as e power x. Okay, it's a non-trivial fact that given this you can prove this, but at this point it's okay to take it as a memorization also, that this is true. So this gives e power lambda, which explains e power minus lambda. One more property of exponential. It doesn't have to be e, it could be anything, a power x, etc. But this is kind of cute. It tells you that if you want to know what e is, it gives you an infinite series. Put lambda equal to 1. So 1 by n factorial. So suppose you want to get e to 10 decimal places, you can figure out, you go up to some term and you're done. Okay. So this is called the Poisson distribution. Okay, good. So I'll give you a third example, which is a completely distinct nature from here, in the sense that S will be the full real line now. Okay. So what is the third example is called the Gaussian Yeah, go ahead, ask the question.
So where do we see examples of Poisson distribution?
Oh, that is my second lecture. Everything we are seeing here, I have a hidden agenda, which is lecture 2. Right now it looks like some random mathematics, which it's not. Okay, so is the real line. It has two free parameters, mu and sigma. Okay. Okay. So the easiest thing is to plot it. Say when mu is 0, I'll give you a plot. Okay, it's a nice smooth function, peaked at 0. For other things, it's shifted by mu, the peak would be shifted to value mu. So mu can be any value from minus infinity to plus infinity. So, and it is symmetric because of x minus, it's an even function. And it goes to 0. Okay. The catch here is, what does it mean that total probability is 1? It's taking continuous values, so you can't do summation. But you do the next best thing, integration. Okay, so Okay. So this is not called probability, but it's called probability density, because it's measured in it's like times dx is probability. Okay, so this is called. Okay, good. So, in your mind, you shouldn't worry too much about the distinction between continuous and discrete, which was the first two examples, in the sense that it's simple. You just replace summation by integration. That's all. Let's not complicate things further. Okay. So that's what we want to do. And so the idea is the last one is something called the expectation value. Okay. So the idea here is the following. So I have a random variable x, and I can take, I can write something like x power n. By that, really, what do I mean? If you give me, if it takes value little x goes to x power n to the nth power. Okay. So we can also take linear combinations, etc. But let's just take something like this. And the symbol which is used, so I will write e of x power n. This is the engineering and mathematics notation. The physics notation for the same, they're equal, is to write something like this. Okay. And this is equal to, now its definition. X power n times weighted by the whatever is the probability. Okay. So one more property, suppose we have some f of x, which is some polynomial, say of degree m. X power I with some ai, you can see that I can just do the same thing out here. Key point is it's coming linearly out here. So I can go ahead and substitute this here, and it's easy to check that this is equal to just look at the definition. So the expectation value would tell you that you just put this function here and then you weight it by this. And for continuous, you just replace this by integration. That's all. Okay. So now suppose we want to write a function which will count the number of heads in n coin tosses. X won't work, but x plus. So I should do something which will map x to 1. I told you to do and tails to 0. Okay, and that would be the map which is 1 minus x if you think about it. Okay, so number of heads. If you want to do, it's nothing but to ask what is the. So this we will call, this is the idea of average number that you would expect. So average number of heads will be equal to, what should I write now? Expectation value of 1 minus x, where x is that variable which we define in the binomial. Okay, and we can do the calculation. What is the average number of heads in this thing? We know how to, we just follow this formula. It says do this summation, little x goes from 0 to capital N into 1 minus x into what did I do? 1 minus, yeah, that's okay. X goes from 0 to n, 1 minus x into n, choose x but I think you know the answer to this. What is it? No. N into P. NP. You can sit down and prove it. It's not so hard, but this is something you might know. Okay. So this is the answer for the binomial. Okay. And I'll give you the answers and leave it as exercise for you for Poisson. You get mu. And for Gaussian, also you get mu. Okay, so the symbol mu is used to denote average or mean value. So it's the mean value of something. Oh, I'm sorry, this is not correct. This would have been for x. Okay. For 1 minus x, you would get n into 1 minus p. So, but you get the idea, right? How you go about doing this. By the way, this integration is a non-trivial integration in the sense that it involves a trick. No amount of substitution of the kind we do to do integrals work, which we learn in high school. If you haven't done integration yet, it's okay. But you will have all these substitutions you will do to do some integral. None of those things work. No elementary computation of this will work. There's only a trick. Either you know the trick or you don't. So there is no sort of badge of honor in saying I know how to do this integration. You go learn it someday. But I don't need it. Okay? So another 1 minute, I'll be done with lecture 1. So sigma square comes, so sigma is some positive number, yes.
So does it work for all the parameters?
Yes, all values of sigma. Sigma also takes values from 0 to infinity. So what sigma measures is the spread. So as sigma becomes larger, it becomes wider. As sigma becomes this thing, and there's a singular limit you can take, sigma tending to 0, which will make that function be 0 everywhere and takes infinity at this thing. It's a weird function. It's not a function at all. So that limit is singular, but we know how to handle it. So sigma in principle can take values from 0 to any positive number. Okay. Because minus doesn't make sense because it comes only through sigma square.
And the integral still remains.
Oh yeah, everything. It's perfectly convergent. Everything works. Very nice. Okay. So the second expectation that I'll do is I will not do, but I will just tell you. So mu means mean. Okay. So this just means expanding it. This quantity also has a name for any random variable. Okay, and it's called variance. It measures how things they change as you go away from the mean. Okay, remember I told you in the Gaussian it measures the spread. So this is what measures the spread. But why this funny combination? Why not something else? Okay. And this has to do, I mean, if I had time, I would talk about the property of this. What it says is that if you have two random variables and which are independent, the variances add, the mean adds. So suppose I have Z equal to x plus y. X and y are linearly independent. Factorization of everything. What this says is that, first thing it says, this is easy, trivial. By using factorization, we can prove this. This says that mu z equal to mu x plus mu y. Now comes the fun part. If we can also prove variance is additive. Again, this is something you might have heard, take the square root, it's something called standard deviation. Again, this is taught to you in this thing. So I told you that the spread of certain, I told you that the spread, you have to do some root n, etc. If you compute sigma, you will see that it will give you root n. Okay, so what it says is that this is the first estimate of how things deviate from the mean. So what you would like to say is that mu plus or minus sigma is probably a better way of understanding where most of the probability will come. Most of the events will fit into that. Okay. So this particular combination is special. So there are many other things with higher powers. So this is like 2, 3, 4, so on and so forth. They have some name called cumulants, and they have the property that if two random variables add, their cumulants add. Okay, so this is, we are saying x, y are independent. Okay, so here I can, if I put 2, that property is messed up. If I put any number other than 1, it doesn't work. Okay, in this way of writing. Okay, and don't think that for higher powers it works. It turns out for x minus mu whole cubed works, but x minus mu power 4 doesn't work. Then there are some corrections. Okay, but it's just, I'll stop here. But this is just to give you some reason why this is defined. The intuition is that you're asking for how things move away from this, and but it also has this additional thing, it's x and y are independent, this holds. Okay, let's take a break.
SwayamPrabha, Digital India, Educated India.